So the expected value is this, and then I can also write that delta, if I said delta equal to 1, then this is true. So actually, xij is actually in the set minus 1 over n, 1 minus 1 over n, which is a subset of, minus 1 to 1. So it's in this range minus 1 to 1, which is all I need. So you can make the bounds a little bit tighter, but it's not going to matter. All right. Okay. So now I have the expected value of 0. This delta is equal to 1. So now let's plug this in. So mj is now actually going to be the sum over j equals 1 to k of xij, which is going to be the same thing as the frequency fj. Right, so now I've retrieved the frequency, and now I can say something about this frequency. How far it's going to go from, well, no, this is not the frequency. If I summed up the yj's, that was going to be the frequency, right? So if I summed up the yj's, that would be the frequency. If I summed up so this is going to be equal to fj minus k over n, which is the expected value of the frequencies, right? So I wanted to say something about fj minus k over n here. Now I have this as mj. Okay? So this is good. So now let's try plugging this into this expression and see what happens. So the probability that mj is going to be greater than alpha, so what should I pick for alpha? Let's say that it's going to be epsilon times k. We'll see if this works out. Which is going to be less than 2 times, and this is going to be alpha squared minus alpha squared, the epsilon squared, k squared over 2 times r. In this case, r is going to be equals to k. And delta was 1, so I don't have to worry about this delta. Okay, so I can set this, I can cancel one of the k's here. All right, so good. So now I have this thing written in terms of this exponential. So what does this mean? Well, so typically how you use this is you want to say this is the probability I'm greater than some error. Okay? And I want this to be small, so I'm going to set some parameter, say some probability, some delta probability of failure that I want, and then I can solve for the value of k in terms of these parameters. So I'm going to say that I want this to be less than some delta. I think of delta as say 1/10 of 1%, or it can be 1/100th of 1%, and we'll see that this becomes small. Okay, so now I have this expression, and I can solve for the value k. Okay, and this should look like, let's see if I can do this on the fly. You're going to get natural log of 2 over delta. Okay, so what's going on here? So if I want epsilon to be, so initially wanted the bound, I wanted this expression to be small. If I want to look at pj, which I said I want to analyze, this is actually going to be Pj is Fj over k, and 1 over n is going to be Fj over k. So if I had set instead xij to be this divided by k, or this divided by k, it would divide on both sides of this greater than equal to something. So then I would have had the probability, so if mj, so if I write up, but I put it in blue, so I do mj over k, right? This is going to correspond with the difference in the empirical probability from the expected probability. Mj over k is going to be this quantity here. And I want this to be less, so if I divide this by k, I can do that on both sides, the probability stays the same. I'm dividing from both sides of an equality, and I get some parameter epsilon, some error parameter I get to choose. Okay, so this is my, something like my 1% error. So I want 1% error on the probability, so I can plug in this expression, and it's going to get the same result here, the same expression. So if I want 1% error on the probability, let's plug in some example numbers here. If I set epsilon equals to 0.01, and delta equals to 0.001, it's small, then what I'm going to get is 2 over 100 squared times the natural log, and this is going to be times 2,000. This is not over 100 squared, it's 2 times. So I'm going to need something like 20,000 balls to get 1% error, times something for the probability of failure. This log of 2,000, natural log of 2,000 was at probably 10. So this means I'm going to get, in order to get 1% error on this balls and bins thing, I'm going to need 200,000 samples, 200,000 balls to get 1% error, which is a lot. Yeah.
The expression mj equal to sum over xij, j should vary from 1 to n, not 1 to k.
So j is, no, so this is going to be for, this is for, corresponds with sample SI. SI is drawn from the set K. There are K values of SI. So each of these are a ball. Each of the SIs correspond to a ball. Yeah.
But it seems like the two inequality are not identical for the second case. The factor 2 is below the denominator.
Yeah, so the difference here is that here I have a delta on both sides, so the difference, the gap between these is 2 delta in this case. It's a little, might be a little confusing, yeah. That's what's going on there. So the first one is just strictly more general. And you can actually tighten the constants in these a little bit if you're really careful on the analysis. Okay, so but I want to focus on this expression here. And so this is, this comes up a lot in like these learning rates. In order to get a certain amount of error, you need to do kind of this 1 over the squared of that error samples in order to get this. This kind of corresponds with, so if we're over here, we had k equals square root n to get a collision, n log n to get the first all non-empty, and I'll try and convince you that this should be roughly some constant times n squared in order to get everything equal. That's kind of what's going on here. So we have the square root n, n log n, and n squared. Okay, so why is this So I'll try and convince you now that this k, this 1 over epsilon, so 1 over epsilon is going to be roughly some constant times n. If you do this, then you're going to have, then in this case, the epsilon k should turn out to be a constant if I did this. So if I do this, then k is going to be roughly c squared times n squared, right? Because k was roughly 1 over n. So if I plug this here into this air, the probability that it's greater than so then epsilon k is going to be here. It's going to be so if I want this to go small, then I need to set, if I want this to go down with k, then I want epsilon k to be roughly this term within, if I write these both in terms of n, I get c squared, n squared over Cn, and this is going to be roughly C times n. So for any constant, this quantity is going to grow. Okay, but if I instead, and remember this quantity corresponded with the counts here, which is the number of the difference between the balls in the bin, in the counts from the average. If I look at the probability instead, then I'm dividing through this quantity by k, and then if I want this to be small, then the epsilon quantity is actually going to be. And in that case, the epsilon is going to be 1 over square root of n, roughly. 1 over c times the square root of cn. Okay, so then as n grows, this quantity is going to go down. And it's going to be independent of, the air is going to be independent of, so here the bound I had depended on the number of samples I had, which is why it seemed kind of weird. This probability one is going to be much more natural. Okay, so this was, okay, I apologize. I don't think I made a very convincing argument here why this is roughly n squared. It's not an exact match where these other two quantities had this event that was happening. This is more qualitative bound with these two parameters. But this expression where you need roughly 1 over epsilon squared samples to get an epsilon fraction of the error is something that's going to come up. Okay, so all right, so let's take a step back and say, one thing I wanted to show in this expression here was bound this probability bound. And I said I want to take the maximum over all these values j. And here I said for any one value j, that this error bound I could get to be smaller than epsilon with some probability dependent on delta. Okay, I could get the probability that it was greater than this over k was greater than epsilon was going to be less than whatever parameter delta I set here. But this was for a single one of these j's. Okay, this was for a single j. I want to take the maximum for all j's. I want to say all of the bins have small error. Okay, so this is something that's often ignored if in certain types of scientific analysis. Okay, so there are these. So a lot of people see in statistics they'll calculate these p-values, and I'm not going to concretely define p-values. If you know the exact definition, it's a little bit more complicated than it's not just the probability of a failure, but it's related to these sorts of quantities. But it's kind of saying if you run this experiment independently, the p-value is the probability that you would recreate this result at random. And so in a lot of scientific tests, there are many people looking at the same data running experiments, and so if p-value is 0.01, it means if I ran this 100 times, I'd maybe expect to see it once. It doesn't exactly say that. But that means that if 100 scientists are looking at the same data set, maybe one of them will find something that has a p-value of 0.01 that wasn't actually a real phenomenon. It just happened by random chance. And this is similar to looking at these balls and bins and saying, what's the probability that I had way more balls than I expected, that one of these bins was special, right? And that's saying the maximum here, the bin with the largest deviation is large. I've said here, I've bounded using this Chernoff-Hoeffding bound, the probability that one of these, that if I just looked at one of these bins, this one does not deviate from the average. But if I want to look at the probability that none of them deviate from the average, I need to somehow combine these results together. And so in order to do that, the typical way of doing this is the second kind of important theorem I'm going to talk about today. And this one I don't think is actually attributed to anyone unless there's some very old mathematician named Union. But it's typically, the union is like the union of sets. I don't think that's a name. So the union bound tells you how to combine together these different random events, and it's often used in conjunction with these Chernoff-Hoeffding bounds, where this tells you one event, and this tells you how to combine these events together. Okay, this one required all the events to be independent of each other. The union bound is not. Okay, so let me write this up. So let's say Z CT, let's say T, D, T, random events. So when I say event, I generally mean it's a random variable that's either 0 or 1, where it's true or it's not true. So Z I is going to be 0, is going to be in the set 0 or 1. Okay. Where you can think of, if we're computer scientists, 1 is true, 0 is false. So now, I want to say the probability that all Zi are true, so the probability that all these events occur is going to be equals to 1 minus the sum equals 1 to T. One minus the probability that Zi is equal to 1. so this is, I'll show how to apply this in a second. This is on the bottom of the notes here. This is not hard to see is true either. It seems like it's a pretty sloppy bound actually, if you think about it. You're trying to say the probability that all of these are true. That means that none of the events are false. Okay, so this is the probability that, this is the probability that any one event is false. And we're taking the sum over all these probabilities. So I'm adding them up. Often, if they're independent, you can often do something by multiplying events. But I'm just adding up these probabilities. It's quite possible that these events are actually going to be correlated, and so that the sum is going to be an overestimate of the probability that they're not true. So this is the probability that at least one of the events is not true. Okay, so you can think of, geometrically, you can think you've got some probability space. Okay? So this is the probability that event 1 event 1 is not true. It's the probability that event 2 is not true. And so the whole rectangle is equal to 1. This probability that event 3 is not true. So if I sum up all the probabilities that they're not true, that's the union of these circles. But actually, I'm just going to take the sum of the individual circles. So that means even though there's this little overlap here, I can count that twice. But it's going to be an overestimate. Sorry, this is an inequality. So I can count that twice, and that's still okay. The probability that they're all true is going to be everything outside of these circles. And I'm gonna upper bound this quantity by taking 1 and subtracting each of the circles added up individually. So this picture is the proof. This is basically.
So if you're ignoring the intersection, doesn't it mean that the variables are dependent?
No, it doesn't mean that the variables are dependent, but
Are independent.
no, it's a worse bound if I add them up twice. If they are actually independent, that means that if the variables are independent, it means that if I just look at z1 and z2, that if I looked at the fraction. So what that would mean is that the fraction of z2 that intersects z1 is proportional to the fraction of z1 of the entire probability space. So let's say that z1 is 10%, z2 is 10%. If they're independent, that means that this intersection would have to be only 1% of the probability space. That's what them being independent would be. So it would be independent. So knowing this one was true, this one was false, would not influence whether probably this one was false. Actually, if you look at the very end of the notes, I have some argument that even if they are independent, you're going to get a fairly similar bound in most cases. So losing the independence does not is not going to lose you too much here. But so. Now the reason why their non-independence is going to be important is because we're going to look at all the values j, and these are not going to be independent of each other. In fact, if one bound is small, the other bounds are actually more likely to be small, as it turns out. Okay, so let's see how to apply this here. I want to say instead that the maximum here is going to be this. And so instead of saying the maximum, I'm going to say all of them are true. Right? So so I want all of these events to be true. The event that I want to be true is actually going to be the opposite of this event. So this is saying I have more than so much error. So I want there to be less than this much error. So that's the event I want to be true. I want to have small error here. So that means 1 minus this probability, or so 1 minus this probability is what I'm looking for. And actually, this is going to correspond to the event probably zi is equal to 1. And 1 minus something is going to be back this again. So, okay, so I want, let's try and write this down. So I will say zi is going to be the probability that this value, this empirical probability minus 1 over n, that this is going to be less than epsilon. Right, so if I divided through both of these by k, then this is exactly what this says. Or that this is the opposite of that event. Okay, and I set this quantity equal to, this was bounded by delta, so I want, so if I say this quantity is equal to, so this was, use j here. This was equal to 1, it's equal to 1 minus zj. It's equal to this. And so I have 1 minus zj is less than, this quantity is less than delta, where delta was this bound here that I can plug in this expression, okay? So now I want to use this union bound. And so 1 minus zj is actually the term in the sum here. So this is actually convenient. So it's convenient to prove it this way, that the probability exceeded my error. So 1 minus zj is less than delta. That means that the sum over j equals 1 to n of 1 minus zj is going to be less than or equal to n times delta. Okay? So now I can use the union bound to say the probability that all, so that, let's say, all j in n of pj minus 1 over n is less than epsilon, is less than 1 minus n times delta. And so this probability is the same as the probability that if they all satisfy this, then it's the same as the max of j. The worst case one, right, so now this is less than epsilon. Okay, so these are equivalent. And I bound this by 1 minus 1 over n delta. Okay, so now I have this extra n term over here. How does this fit back into this expression? Well, I wanted some delta probability of failure. So now let's say that I want the probability of this to be less than some quantity 1 minus, let's call this probability delta prime. Okay, if I want this delta prime is equal to n times delta, then I fit in this expression. I can set k equals to 2 over epsilon squared times the natural log of 2n over delta. So what did I do there? I wrote out let's see, so how did I do this? So I'm going to use that n times delta is equal to delta prime. I wanted this, So I actually want the probability for all of these to be less than, delta prime instead. So I plug delta prime into here, right? And this means that, so if instead I want this n times so then I put delta prime. Yeah, okay, good. So then I can solve for delta equals delta prime over n. Okay, good. So if I can bound this in terms of delta, when I plug delta into here, I actually want to get a delta prime bound. Delta prime needs to be n times delta, and you get this extra n. Okay. So what's happened? When I got this to be true for all of the n instances, all of these different bins, I have an extra n inside this log factor. Okay, so this actually is good news. Okay, so I want it to be true for all of them. I have to increase it by some factor that depends on the number of bins. But it's inside this log factor, so it does not have a very large effect. If I already had a value, if 2 over delta before was something like 2,000 and I had 100 bins, then it's going to be 200,000. But the natural log of 200,000 versus 2,000 is off by, what is that, like a factor of 3 or something? So I need a factor of 3 more balls to get it to be true for all of the bins. If the n came out here was a polynomial factor, this would be a big deal. Okay, this would be a really big effect. But it's inside of this log, so it's not too large of an effect. The other good thing is that, so even if the number of, so often we'll see these things where the problem size is going to grow as a function of n, and the number of things we want to test is not just linear in n, it could be some polynomial in n. You may have something like n squared or n to the third, different things you want all to be true at the same time. If you plug, so in order to do that, to get them all to be true, instead of testing for n things here, you have you'd have an n cubed in this spot. And then this would go to be an n cubed. But inside of a log, just to illustrate how useful it is inside the log, if you have a cubed here, you can basically take rid of this cube and move it out as a constant factor 3 in front. Right? So powers inside of a log are constant factors in front. Right? So log of n to the c is equal to c times log of n. So increasing n to any polynomial, the polynomial power becomes a constant factor in front. So it's still, you're still getting these factor 2 or 3 more balls that you need to throw into the bins, but it's better than having a factor 100 or a factor 100,000 more balls you need to get the same effect. All right, so the hope of this lecture was to try and give you a first look at these two important bounds. This says you have a bunch of these independent random variables, and you're going to estimate based on the sum of these random variables. You can bound this with this Chernoff bound, and this fits this theme of you have a bunch of these simple estimates. Each of these estimates is a single ball. Okay, I want to estimate the probability that a ball falls in a bin by throwing in a single ball into that bin. Okay, and I'm going to repeat this process by throwing some large number of balls. and then I can aggregate these probabilities together and get a very tight estimate. Right? So this is a very tight estimate of the expected value. So this is kind of the first taste of this process. The other thing I want to show is that if you want this to be true for these kind of expressions where you get this 1 over epsilon squared, this is going to come up in several types of analysis later where you want some small percentage of error. That's going to be this epsilon term here. And you're going to need roughly 1 over epsilon squared steps. And so this is, so I proved essentially an upper bound on the number of balls you need to throw in here. This bound is actually pretty tight. I think you can probably get rid of the factor 2 here by some more careful analysis. So it may be roughly 1 over epsilon squared with the log factor here. But you're not going to get rid of this 1 over epsilon squared term here. For a random process, you're going to need roughly this many instances to get epsilon error. The interesting thing is this n term inside the log. For a lot of these sorts of things, there's some classic results from learning theory that are able to get rid of this n term entirely by showing that balls in bins poem and much more general things like this are, because the events are negatively dependent, if one bin is accurate, the other bins are also more likely to be accurate. You can completely get rid of this n term inside here. It's really tricky to understand that. So if you're taking some machine learning, this is based on classic results by Vapnik and Chernoff-Hoeffding, and there's this Vapnik and Chernoff-Hoeffding dimension. And so it applies to some much more complicated sets of problems where you can completely get rid of this n term here. All right, so this expression and this sort of analysis where you can combine together these events and then get it to hold for all events is going to come up in a few of the other algorithms. The first iteration of the class I taught